This is about trying to solve problem 12-170, which you can see on the screen. It says a particle is moving along a circular path having a radius of 6, such that its position is given by theta, and everything's in radians, etc. What they want is the acceleration of the particle when theta is 30 degrees. They give initial condition that starts from rest when theta equals 0. Okay, to begin this problem you need to decide what coordinate system you plan to use. I like to start and rule out tangent normal, and I do that if I have no information about speed or change in speed. In this particular case I don't have that information, so I'll go to the second choice, which is r theta, transverse radial directions. Here I need the radius and angles, which are given to me. So it seems obvious to me that this would be a radial and transverse problem. So I'm going to start with that. Okay, so what I'm going to do is write down the things that I know. They say it's a circular path with a radius of 6, so I'm going to say that the r is equal to 6. And this will be in inches, so I need to be careful with the units. Because it's a circular path, the radius is constant. So if r is constant, I know that r dot is 0. If r dot is 0 all the time, then the change in r dot, r double dot, will also be 0. So I know that. The next thing that I know is they tell me something about the angle theta. So for example, they tell me that theta, which is in radians, is equal to the sine of 3t, and the 3 would be in radians per second. Okay, so in order to use the formulas, I need to know what the acceleration formula is, so I'm going to write it down here so I know what I'm looking for. The acceleration then, using r and theta, is equal to r double dot, this comes straight out of the book, minus r theta dot squared, and this would be in the radial direction, plus it's equal to 2 r dot theta dot plus r theta double dot in the transverse direction, or the theta direction. Okay, so basically what I need is I need the values of r dot, r double dot, theta, theta dot, and theta double dot. Well, the r's I've already gotten, so all I really need to do is to find the derivative of theta. So I'm going to go in and do that. So d dt of theta is equal to, and so I'll just take a derivative. The derivative of the sine is cosine, times the derivative of what is inside the argument list, so times 3. So that'll be the derivative of theta. So to simplify just a little bit, this would be equal to 3 cosine 3t. Okay, to take the second derivative, I'm going to take the d dt of theta dot of what I just took. So in this particular case, I have the derivative of the cosine is minus sine, so this would be minus the 3 out front, the constant, sine of 3t, times the derivative of what's inside the sine term, which is 3. So this is equal to the theta double dot, and just to simplify a little bit, that'll be 9 minus 9 sine of 3t. Okay. Okay, so in order to have these values, I need to have the value of time, which I don't have, but they do tell me that the time that they're interested, they say that theta is equal to 30 degrees. So what I'm going to do is I'm going to say 30 degrees. And because the equation for theta is in radians, I need to convert 30 degrees into radians. So what I do is I say, well, there's pi radians in 180 degrees. So now I have radians. And that will equal the angle theta, which is equal to the sine of 3t. Okay, so basically this last equation gives me what I need to find t. Once I know what t is, I'm going to substitute that in and get theta double dot, and then get theta dot. I already know theta, and then I'm just going to plug directly into the acceleration equation. So I plan to pause at this point and pull out a calculator and do. I did not have my calculator with me, so I put this into Mathematica. Rather than bore you with trying to type things in, I typed it in, and here are the results. So the first thing I do when I open up Mathematica is I quit. This makes it forget anything that I've been doing in the past, so that I know I have a fresh start. First thing to do is to solve your equations for t, which is what I do here. The numbers that I was given in the book as theta was equal to 30 degrees. I converted it into radians and then solved for t. Then what I did was I just simply copied and pasted the answer for t, and I pasted it in down here. Mathematica, even though it only shows you 5 digits, it holds a lot more digits, and so when you paste it, it just comes out with all of this extra digits. And then all I did was I typed in the equations, or the values for theta dot, theta double dot, r and r double dot, etc. So I typed that in and execute it. And then here are my equations for the accelerations in the radial and the theta direction. So it's going to take those values from above and just punch them in. See, these are the values that I get. And then they're looking for the acceleration, or the magnitude of the acceleration. It wasn't real clear in the problem, but when I looked at what the author was really looking for, he wanted the magnitude. So here's the magnitude. It's the square root of the sum of squares, which ends up being 48.33, and this would be inches per second squared.